Modern war often demands the massed fire of a battalion or group of battalions. For maximum accuracy, the relative velocities of all weapons involved must be known. Even new guns may not have exactly standard velocities, and in combat use, some guns will wear faster than others. Calibration is the process of determining relative velocities. The necessary calibration can be done by observation of the impacts or bursts. Then the observed differences in actual range can be converted into velocity differences by use of the firing tables. But here's something new. The Ballistic and Technical Service Team. It is highly mobile and has been trained and equipped by the Ordnance Department to calibrate your weapons faster and more accurately by direct measurement of velocity. In the field, this team of 2 officers and 11 enlisted men splits up to form 2 self-contained units. One unit works at the front, and the other stays back at a 4th echelon shop. The outfit is complete even to a shop truck with all necessary maintenance facilities. 2 generators supply all electrical needs of both units. One generator is in the 1-ton trailer and the other in the shop truck. This team comes to you ready to work. It can furnish exterior and terminal ballistic data, but the main job is velocity calibration. Each team carries 2 different types of chronograph for measuring velocities. First, the Aberdeen chronograph. 2 of its elements are these wire screens mounted in simple wooden frames. The screens are set up in the gun's line of fire. The first screen is 75 or 100 feet ahead of the gun, and the second is about 100 feet further out. The projectile, passing through the screen, pushes the wires into contact and closes the electric circuit. Cables connect the screens to the recorder, which remains in the shop truck. Here it is, the Aberdeen type recorder. A strip of waxed paper goes inside the metal drum to be held in place by its high speed of rotation. From that movable arm, a spark will jump through the paper to the drum when the circuit is closed by a shell's passage through either of the 2 wire screens. The gun fires and the shell hits screen 1 and then screen 2. As the shell goes through each screen, a spark jumps in the recorder, marking the waxed paper on the whirling drum. The size of the drum and its speed of rotation are known. So is the distance between the 2 wire screens. Therefore, a precise measurement of the distance between the 2 spark burns enables the computer to figure shell velocity between screens and assign a definite muzzle velocity to the shot just fired. Altogether, 6 rounds are fired to get an average. This Aberdeen chronograph is usually used by the rear echelon unit to calibrate new and reissued guns. The other type, used by the forward unit, is called the telephoto pickup and counter chronograph. This new equipment will do the lion's share of the work in the field. Telephoto pickups take the place of the wire screens in front of the guns. The shell doesn't hit these pickups. It passes over them and is almost literally seen by them. Here's the first pickup. The second is being set up 100-odd feet further from the gun. The small horizontal tube is a sight used to orient the pickup with the gun. The round central body of the instrument is a telescope. You can see the big objective lens on top. In the base is a photoelectric cell which receives light from the sky through that lens. When the shell passes over, the cell reacts instantaneously to trigger a circuit. A gunner's quadrant is used to tilt the instrument perpendicular to the shell's line of flight. This is the complete setup. Here's the gun, and here are the 2 pickups. They're connected to the counter in the truck by cables. When the gun is fired, the projectile follows this line of flight. As it passes over the first pickup, it starts the counter. When it passes the second pickup, it stops the counter. The time required for the projectile to pass from one pickup to the other is recorded by the counter. This is how it works in practice. The gun is fired. The shell passes the first pickup, then the second. In the truck, the time interval is recorded in lights on a panel on the face of the counter. These lights give an immediate reading of the time interval in 100,000ths of a second. From this figure and the dimensions of the pickup installation, a muzzle velocity is computed. Then the circuits are cleared by tripping switches, and another of the 6 record shots can be fired. 2 counters act as a check on each other. That third one is a spare. A battery can, if necessary, be calibrated in half a day in its regular combat position, providing the team can work in daytime. But the pickups can't see at night, so if it's impossible for the teams to do this work in daylight, the instruments could be set up under cover of darkness and the guns fired the next morning. In this case, the entire job would take 2 days and 3 nights. There's another, faster method of handling this job, a method which will be used whenever possible. The guns are lined up in a tandem formation, one behind the other and all facing the same way. Here's the truck and trailer. The entire apparatus can be set up and adjusted in half an hour, including the pickups, which are placed in front of the leading gun at the usual intervals. They're connected to the truck by cable. The rear gun fires its shots first, the shells passing over the rest of the guns to reach the pickups. Then that gun can be pulled out while the next gun is fired, and so on up the line. With this system, an entire battery can be calibrated in about an hour. Many batteries from 90 to 155 millimeter will be handled in this way. But the bigger 8-inch guns and 240 millimeter howitzers will usually be calibrated in battery position because of the difficulty of emplacing them, unless there is an opportunity to calibrate them in a rest area. Whatever the method used, remember that this is relative calibration. It can be done with any available ammunition lot. If another lot were used, the velocities might be different, but the velocity differences between guns would remain the same. So once a battery or battalion has received relative calibration and one gun has been adjusted onto the target by observation, it is then possible to put the other guns on target immediately by allowing for the differences in muzzle velocity. So you can see that relative calibration is an important aid. But efficient battery or battalion fire depends on many other factors, such as keeping weight classifications and ammunition lots straight, having good storage conditions, accurate meteorological messages, and good observation of fire. In brief, the ballistic and technical service teams can provide accurate data on the velocities of your weapons, but they cannot take the place of care in following the details of artillery doctrine.